To the Tuesday afternoon track one session, successful strategies around autonomous plants. Now we've got an all-star lineup of speakers here for you, so we're going to get started on time, okay? For those of you that are observant, this is not a picture of me. It's not Mark Semgupta, who didn't age well. Mark called in sick. We're glad that he stayed home. It's because he's sick. I'm Paul Steinitz. I'm with ARC as well. Okay. A little bit of housekeeping. I shouldn't have to tell you, but please silence your devices and leave them on because you might want to interact with the feedback on the session at the end. And check your app for updates. And one more time, please silence your devices. Now, we are all engineering technical people, so risk management is something that's ingrained in us. So when we hear something like, would you get into an autonomous car, we all cringe. So it's all about risk management and the reward that comes along with it. So even if, you also might cringe at who's driving the car that you're in, but it's all about risk management. Now, what we're trying to do is improve business performance and the challenges of operations lifecycle. So there's a lot of different challenges. Some of them are tough to meet, but this is not rocket science. It's tougher. Rocket science involves rules of nature, rules of physics, but we're dealing with other things. We're dealing with people who do not follow rules of nature, rules of physics. So we're chasing a moving target that gets tough. So how does autonomous operations help? Well, you can see we're taking the human out of it. We're taking the human error out of it, we're taking the human out of harm's way, and we're saving manpower. Now, you could also use these same bullets for why do we automate anything? We're trying to take the human element out of it, we're trying to reduce waste, we're trying to create efficiency. Now, the autonomous operation is not an all or nothing. You could be completely unautonomous, that is, you're doing everything manually, or you can be completely unmanned. And there's many levels in between, and some of our speakers are going to describe some of the strategies to do that. Hindrances, what are the obstacles? ARC does surveys on all of this, and these are some of the obstacles that we face. They're tough, and a lot of it is money. A lot of it is how much talent do you have? Do you have the right people to support this? So the obstacles are tough, but fortunately, as I said, we have an all-star lineup to tell you about how to overcome these obstacles. Okay, these are the presenters. Well, I'm not going to give you all of their bios as I introduce them. I'll give you the name, their company name, and what their job is. But if you want to know what their background is, use the app. Okay? With that, I'm going to introduce the two gentlemen from ExxonMobil, Dave Hedge and Steve Bitar. Come on up on stage, guys.
Quick check. Okay, good. Hey, thanks. We're tag teaming this, so Dave's coming up after me. It's wonderful to see so many friendly faces here after two and a half years. I wanted to spend some time today speaking with you about control system infrastructure that supports autonomous operations. So I want to make that clear. I'm not going to be talking about autonomous operations because that'll be covered in the next two sessions. We're talking about the infrastructure. So my opinion, the control systems that we use today are beautifully engineered. They're very, very reliable. I would even say elegantly designed. But they are going to struggle to get you past level 3 autonomous operations in their current state. For that, we are going to need a next generation system. So I have a list here of characteristics that would describe what we think are going to be required in the next generation system. I'll go through them really quickly. So some of these you've seen before, they're really common themes. You need interoperability and portability, and those things are very important in any architecture because you need to be able to insert your technology and reuse it. And you need best-in-class or a fit-for-purpose design. But the other thing is a common theme I've been hearing about this week is everyone talking about no one builds everything to do everything for everyone. So you're going to get by on with a little help from your friends. You're going to need this capability to insert technology to get the right components to make things happen. You also need access to sophisticated software development tools because you want efficient coding, you want good code quality, and you want to eliminate all the barriers to innovation. And you want access to libraries too, rather than writing everything from scratch. You want interchangeable edge devices. Because if you have any need at all to replace your hardware, maybe you just need more compute cycles, or maybe you have a cybersecurity vulnerability, you want to be able to pull it out and replace it with a modular component. And that's kind of the inspiration behind the Far Edge Open Compute Interface standard, the Focus standard. If you're interested in that, Intel has an ExxonMobil Georgia Tech Research Institute demo set up later today you can take a look at. And the last one on the list is high availability. So there are kind of two things we were looking at here. One is be able to configure our fault tolerance, and the other is a common failover service. And I'm going to explain exactly what those things mean. And this probably goes without saying, but we clearly have to do this without compromising process safety. So I could spend hours talking about each one of these in great detail. Unfortunately, we only have about another 17 minutes or so. So we're going to pick one, and we're going to talk high availability. So quickly. Some definitions: fault tolerance. Property that enables the system to continue running if it fails. So, the great example, the typical example is a tire. You get a puncture, you keep on driving. Good example of fault tolerance. Reliability. Reliability engineers have a strict mathematical definition of this. It's the probability that a component functions for a specific period of time. So if you say, hey, I want this component to be after 5 years, say I have a 1 in 1,000 chance of failure after 5 years, and your reliability at 5 years is 99.9% or 1 in 1,000. And the third term to define is availability, which is a bit different. It's the uptime. It's the percentage of time that the system is available. So if you know you're going to shut down your system, say once a day every year, then your best availability is 364 over 365. Now, if it's unreliable, it's going to get worse. But you can see in that little insert how they're all related. So the availability is affected by your reliability and also your downtime, whether it's planned or whether it's unplanned or repair time. And then your reliability is dependent on your fault tolerance. Of course, the software, the hardware, the components, the maintenance strategy, and other things. But we're going to talk about those three yellow boxes on the left. So this is the math slide. Fairly straightforward, but I'll just kind of explain the general principle here. You have these nodes on the left, those yellow boxes or orange boxes. So you can think of them as like an individual compute node, IoT edge devices, DCS controllers, PLCs, PACs, but they're all the same hardware, they're running the same software, they're producing results, and they should be the same. And you're going to use them as a method of fault tolerance in case one of the nodes fail. So you can do some really simple math here. I mean, the probability of this thing failing, well, every single node has to fail for it to fail. So you just multiply the probabilities of failure together, and you get really simple equations that say, look, I have my reliability of the system as a function of the reliability of each component, right? Just very simple. But we're actually not interested in that for this analysis. We want to flip that around. We want the reliability of the component to meet a target system reliability. So it's a nice symmetrical equation. You just flip it around and you get the reliability of the component. So if I want 99% reliability, I can figure out if I have 5 nodes, how reliable each node has to be. If that didn't make any sense, don't worry, because I have a picture. This is the same thing we were just looking at, except it has the nodes on the left-hand side. And it has the node reliability on the left-hand side on the y-axis. It also has the number of nodes or the node count on the x-axis. And there's one curve up there that says system reliability. Well, that's the reliability of the cluster. That's 5 nines. I use that because it kind of pops up very often in our industry. But there are a family of curves you could draw. All right, so the way this works is if you have one node down at the bottom, you follow that line up. Well, if you have one node and you want 5 nines reliability, that node has to have 5 nines reliability. If you have 5 nodes, it looks like about each node has to have a 90% reliability, right? Why? Because they're 5. Right? You got a lot of backups. So let's overlay what a traditional DCS would look like. You'd have 2 nodes. Each one would have a reliability slightly less than 99% because there are 2 of them. I throw in the mean time to failure in there, but don't take that literally because this doesn't include wear-out failures. It's like saying a human would live to 1,000 years if our organs didn't fail. It doesn't include the wear-out, right? So that's why that number's large, but it's there for relative comparison. Okay, so there's your kind of typical setup in a DCS. But what if you wanted something different? What if you wanted 4 devices, but you still wanted 5 nines reliability? Well, something interesting happens. Now, the reliability of those individual components drops significantly. It goes down to 94% and change. Now, that's going to save you an awful lot of money to buy 4 nodes at 94% and 2 nodes at 99 and change. Now, I'm not suggesting you do this. I'm just saying that what we're going to be talking about is the flexibility to allow you to choose what you want to do and fit it for your particular plant. So you could imagine maybe part of your plant, you don't really care if it shuts down. You can make up the capacity anytime. It's not a safety, not a financial, not an environmental risk. And you just say, I don't want any redundancy there. I don't want to pay for it. Here, I'm a little more concerned, so I want one-to-one redundancy. But over here, this stuff's really critical. I really care about this. I want triple modular redundancy or quad modular, or maybe you want 6 nodes for whatever reason. You do the math. Or maybe you find out that you put in 2 and 2 wasn't enough and they're failing more frequently than you expected and you want to throw in a 3rd. Now, that would be really interesting to be able to dynamically, while the plant is running through an orchestration service, to be able to maybe throw in another device or maybe just reallocate software in another device to serve as that 3rd replica. So this is the thing that we're shooting for, and we would like to see this flexibility to be able to configure your own reliability and fault tolerance. Now, I have to tell you about this. We're going to show you a demo and some results, some lab work that Dave Hedge is going to share in a few minutes. But I've read probably about, I want to say 40, 50 papers on fault tolerance. I'm going to save you a lot of time so you don't have to go through that pain. There are like about 3 different classifications of fault tolerance. The first one, simplest one, it's called fail stop. A device fails, the other one picks up the work. And that's pretty simple to actually detect because you use very simple heartbeat methods. One fails, the other one picks it up. Maybe you have a voting algorithm, maybe you're detecting a loss of a heartbeat, and then you go ahead and pass that information on to the client, whoever's consuming the data from those 2 replicas. The other classification are called, I called them operational faults. You won't find that in any literature, but it's sort of the case where the replica makes a mistake, it does something wrong, it sends a value out, but it's incorrect. And in this case, one of these 3 is not like the other. You have to do some sort of voting, inexact voting usually, and you have to pick, okay, this is the right value, I'm going to exclude that 3rd one because it's just not fitting in. And the 3rd category of fault is called a Byzantine fault, and that's sort of a collection or a bucket for everything else. And that name comes from it's a 1982 paper. It was really describing, I think it was an allegory about the Byzantine army, and you can go read it if you're interested, but it really it captures every other type of fault that can happen beyond these 2. But typically it's characterized as you have some kind of a bad actor that's sending 2 pieces of information to 2 different people. And there is a lot of interesting theory and proofs that show that, well, for a minimum to catch 1 Byzantine fault, you need 4 nodes. And my point here is, you have to decide what kind of faults do I want to protect myself against, understanding your particular process and how you want to manage that risk. But it's not as simple as the way I drew it. Really, where the rubber meets the road and where this gets very difficult and challenging is you need 3 things in order to mask these faults. So number 1, the state between these different replicas has to be synchronized. Number 2, they have to execute synchronized as well because you're going to compare the values. So they have to run at the same time. And the 3rd one is when one does fail, it has to pick up very, very quickly. Now, those things are easier said than done. Synchronization in voting, I'll just delve into that just for a little bit, kind of show you the lay of the land here. On synchronization, most of the algorithms we see today for synchronization, they're proprietary. We don't know exactly how they work, but if you read enough, you can kind of guess how they operate. So you'll have a primary node and you'll have a backup node. The primary node will collect some data, execute some logic, it'll push out some values, it'll synchronize its secondary. So its secondary can take over if it fails. And I kind of call that a series type of synchronization. But this is where it got really interesting when we were doing the research, which is, why can't we do this in parallel? Why can't we synchronize all of our replicas at the same time? If they get the same input data and they have the same application or algorithm, they should produce the same result. Why can't I do that? So you look at this and you think, well, that's a little crazy, Steve, because how do I know that each of those nodes are going to get the data when they're supposed to get it? And the answer lies in the evolution of middleware. The middleware has evolved so dramatically in the past decade or so. It can do remarkable things that you couldn't do before. This is not your father's middleware. So you can set up reliability requirements, best effort, reliability. You can set up latency budgets. You can assign qualities and strengths to your signals. And all this stuff would allow you to achieve that parallel synchronization. And you can imagine how easy that would scale and how easy it would be to implement. And that would lead you down the path of saying, okay, now I can change my mind whenever I want. Because this is more of an orchestration, right, than a rip and remove wires and replace the system because I want to go from dual to triple. All right, so I have to just mention voting really quickly. You have to have an algorithm for voting. The first thing we did here is we had a couple of replicas and we pushed out a value. We published a value. We had a client. And the client could be like an analog output module, a historian, an HMI, anything that's consuming the data. And we wrote some really clever voting algorithms. If I had time, I would love to share them with you. They kind of combine graph theory and machine learning, and they're a fascinating science all unto themselves. But we put that in the client, we did the voting. We're going to show you a demo of that along with the parallel synchronization. But I do want to mention that we did spend a good deal of time thinking about another way of doing voting. And this was kind of motivated by the blockchain technologies where you have all of these nodes that have to come to some sort of an agreement, a consensus, hundreds of them. And how do they do that? There's no one in charge. So we got into this and wrote a couple of algorithms, and we demonstrated this proof of concept that you can do this distributed voting or consensus. And of course, what do? Well, you get your result, you tally your results, you push them out with your answer, and then the client just goes ahead and takes the value with the highest tally. Now, what you've really done here is you've moved voting from the client up into these kind of distributed edge devices that are running your application, your autonomous operations, or anything you want. But the point there is we weren't quite so sure we wanted to burden the client with all that extra compute resource requirement. You don't want your analog outputs to have really expensive, complex heat-generating chips in them. So we said maybe this is a better way to go. But we are going to show you the parallel synchronization in the subscriber voting, at least the output of that. It's my last slide. So this kind of brings it all together and kind of another way of looking at it. So there are two devices here, right? And the way it's set up, we have a platform down at the bottom, and we define the platform as the hardware and the operating system. And then you kind of see some physical connectivity down at the bottom. We have 3 physical layers there. One is the control network. That's kind of like your HMI and your historian. You have the I/O bus for your field devices, sensors and actuators. And then you have this kind of expansion bus, which is a dedicated bus, peer-to-peer bus that would connect all your devices together for a high-efficiency private communications. And then the application layer is where your autonomous operations would execute, probably inside some type of runtime. The middleware is they all provide communication services. But I'm drawing now this synchronization service in the context of this model. And you remember I talked about how most one-to-one redundancy models work. They synchronize state, make sure their secondary and primaries are all synchronized and ready to go as a backup. Well, that's kind of what I'm showing here, that the synchronization service is tightly coupled to the runtime where your applications are. They synchronize each other through kind of logically through that arrow, but physically through that expansion bus. The question we ask is, why can't we move that to the middleware? And that was kind of a powerful question for us because having a common synchronization service gives you a lot of flexibility to scale. But it also allows you to configure the fault tolerance very easily, right? And another problem we realize is, do you really want a bunch of synchronization services attached to every application? I don't even know how that would work in a single device. But really, the message behind that was pay for reliability if and where you need it. Okay, the last point. In order to make this work, you're going to need a middleware on steroids. We made a list of things that the middleware would have to do. These are the basic requirements. You have to preserve the order of the messages that are sent. You have to have some kind of dynamic message priority, which one's more important than the other. You have to have ACKs and NACKs and retransmissions. You have to have heartbeats to ensure liveliness of the nodes. You have to retain message history because how do you add a new node onto a system and it has to quickly get up to speed and get up to state with the rest of the devices. And then all the kind of real-time requirements and scaling. So where on earth are we going to get a middleware like that? Well, lucky for us, Dave Hedge is here, and he's going to give you the answer to that question and take you through some of the results of the demonstration. All right, Dave.
All right, thank you, Steve. So yeah, let's talk about prototypes. So Steve and I like to dream, but it's even better when you can take those dreams and turn them into reality. And so, as we talk through these concepts and some of the things we want to try to accomplish, the first thing we decided is we got to build something. And we got to make it real. So we built this test rack. And the whole idea was, how do we begin to validate the concept of reliability or configurable reliability on a heterogeneous platform? Meaning, take n number of computing devices, whether they're Intel-based, ARM-based, different types of operating systems, and make them work together to accomplish a goal. The second part that we looked at is, Steve mentioned that the middleware piece. Where in the world are we going to find this thing? It sounds like a unicorn, but we want to explore this concept of open standards communication, applying quality of service to achieve the goals that we have around autonomous operations, around how do we begin to integrate applications together to make these systems actually function the way that we want them to. I'm going to talk through the subscriber-based voting art of the possible that we put together. It was put on top of this platform. It was something that Steve and I dreamed up when he was sitting, in the soccer field with his kid on the phone. And what we really wanted to do was, actually be able to prove it out, but then also begin to progress it towards how do we make this reality? Developing the model, developing the data model for this, coming up with something that is somewhat representative. So it's a simple dynamic process with a sine wave input. It's a stateful algorithm that requires both synchronization and tracking. And it includes, we actually put a simulated fault in one of the nodes. So there is an erratic signal coming in. We're able to detect it, exclude it from the vote, and figure out how we want to do this, how we want to proceed. And we tested it down to about 100 milliseconds. That's just kind of where we stopped at that point. And really, this is looking at how do we begin to build these hardware platforms and these capabilities so that we can deliver and get to this autonomous state. But first, let's talk about DDS. So DDS is where data distributed service. This is where we found all of those attributes that we're looking for around quality of service, around the capability of publish, subscribe, event-driven type architectures. So just like we're doing right now, I'm talking, everybody's listening, you're subscribing to my message and Steve's message. That's the type of interaction we want as we begin to onboard more and more applications that have to interact with these types of processes. The other part that we want to look at is, because it's an open standard, how can we use multiple different vendors to accomplish this? So vendor A and the open source version over here, do they actually work together? Do standards actually come together and make it possible? And the last piece was, let's look at the QoS. Let's actually validate that the pieces that we're looking for are here, or are there opportunities for us to influence and get some of the capabilities that we need potentially in the future to solve these. So I'll walk really quickly through the architecture that we're using for this. It's relatively simple. So we have basically an input coming in. This is where the sine wave generator comes on. And it's a client pair, so we have an AI module and an AO module. Those are really the smarts of this system. The first thing we're doing is all the time-based is on the AI module. So when it scans and actually gets the input, that begins this process of event-driven architecture. At that point, it sends a message up to each replica. Each replica is unique in and of itself. It doesn't know about the environment or anything else in its world. Takes that input, runs a calculation. At the same time, we open up on the AO module a poll for all the calculations from the replicas to come down. They send them inside the voting window. We close the poll, we vote, and then we send the results back out. What this allows us to do is, again, none of the replicas know that anybody's even out there. It thinks it's doing its own thing. It's the only one in the world. But with the sync capability, we're actually pushing back what the winner was, and they're able to correct themselves, as we'll see here in a second. So this is our map of how we went around about this prototype and the subscriber-based voting demo. So on the screen, I'm sure it's small in the back, but this is what it looks like. So up top, the black box is the actual data coming off of the input module. This is running at about 200 milliseconds. It's got a series of different types of quality attributes that we're using. And really what it comes down to is, how do we begin to track this through the system so we don't get multiple values arriving out of sync and cause a problem. So this establishes that event-driven architecture. At this point on, it's all about events flowing through the system and triggering other things to happen. Here's what the compute modules see, or the replicas see. The sine wave that you see, there's actually two. It's a light blue line. There's two of them sitting underneath that, as well as the one that's having the erratic problem. And that's on kind of the AI input signal with air. On the other side, the internal state, we're also tracking the internal state of the calculation. You can see there's a red line, there's 2 there, as well as the orange. That's what we're looking to correct. Without having to tell anybody else or have them know about each other, be able to feed that back and actually correct internally what's happening with this calculation. So how do we do this? We're almost toward the end of the story, and this is where the voting window opens and how we begin to actually do the sync. So we open the vote window, you see 3 values come in. 1, 2, 3. Those are the 3 values from the replicas that just completed the calculation. 2 of them are the exact same, 1 is the erratic. We then close the window after a period of time, and we vote on it. The algorithm picks out 2 that are closest and excludes 1, selects a winner, and selects the winning value. At that point, let's go back 1. The message below is actually sent, and what this message is saying is, I've determined who the winner is, I'm going to publish the winner. Anybody who's not the winner is going to have to recalculate and synchronize in order to make sure that your internal state is the exact same. So what does this allow us to do? We can add, as Steve said, 1 more, 6 more, 12 more. They don't have to know about each other, but they can all remain synchronized in terms of calculation. To demonstrate this, the red box up top is the internal state. 2 of them are the same, 1 of them has a faulty value in it. The next cycle, after that synchronization process happens, you can see that they're all synced. And same thing again and again and again, over and over and over. Now, obviously, you want to correct that if you were in a production setting, but it shows the capability of having devices that don't know about each other actually correct themselves in the field and move us towards this, the idea of configurable high availability across a heterogeneous hardware environment. So what did we learn? It's possible to use a brokerless middleware to do sub-second synchronization. Across Intel and ARM, the replicas don't have any knowledge of each other. They're purely using the middleware to make this happen. There's nothing proprietary. It's all open source, all that kind of fun stuff. We validated the concepts of configurable reliability and subscriber-based voting. I mean, we could add more hardware to this. We could extend it out, all that kind of fun stuff. The other thing is, we also approached multiple workload types. So this is not only doing a control runtime, but the historization that I showed you is subscribing to that exact same data. Everybody is seeing the same thing at the same time, and it's all event-driven. Lastly, we implemented some security into this, so that we are able to make sure that people aren't able to get inside of the messaging and mess with it to the best of the ability as of right now. But that's another area definitely for research. So next steps and where do we want to go from here? And really, it's who else wants to try to work on this stuff? We think this is important. We think it helps us drive towards where we need to be for autonomous operations, especially on the platform side. We want to validate the middleware-based synchronization concept from a scale and complexity. So what happens when you add 2 AIs? What happens when you add more AOs? What happens when you begin to dynamically build the system? How does that work? We don't know. Hopefully somebody in this room has a really good answer for it. Demonstrate real-time distributed voting. Steve alluded to that earlier. What does that look like? How does that change the complexity of the system? What new opportunities does it open for us? And then begin to extend that application voting, which we're currently doing on an application-by-application basis, and move to a device-based polling or voting algorithm, making it part of a common system or common capability of the platform. We don't want everybody to go reinvent the wheel. Give it to us as a one solution, everybody use it, and keep on going. I think the last one is really important for us as we look forward, and that is, how do we begin to integrate some of these native pub/sub capabilities into some of our software products, and begin to move towards that event-driven architecture versus time-driven. And that's, as we look at the strategy and we look at the platforms and the capabilities and the technologies that are out there, how do we begin to coalesce around that and begin integrating those into what the vendors are providing today, so that we can march towards that autonomous concept. We're going to have to integrate multiple pieces of software and hardware to make this happen. So appreciate your time and look forward to the roundtable here in a couple minutes.